I'm Jimmy Youngblood. I'm the Global Geosynthetics Manager here at Solmax. I want to thank you for joining us today. I'm really excited to kick off this first webinar series. The objective of this webinar series is to just get information out to the industry on a lot of different electrical leak location surveys, methods, and information and even experience. I want to thank the speakers, Abigail and Shawn, for really taking time out of their schedule to speak to us today. I'd like to take the time to kind of introduce each speaker. Abigail Gilson from TRI. She spent most of her career at a containment facility and design engineer. Joined TRI in 2012 to focus solely on the implementation and innovation of electrical leak location technologies. She has over 16 years and 170 million square feet of electrical leak location experience, as well as contributing with numerous published papers, seminars, presentations worldwide, and leading ASTM groups on matter at hand. TRI is a world-renowned testing, certification, research, equipment development, and consulting on plastic materials and civil, environmental, and geotechnical applications. Shawn is a geoscientist and development manager at Hydrogeophysics with more than 15 years experience in geophysical and electrical leak location technologies. His expertise encompasses leak location projects at the Hanford nuclear site, in the mining industry and many other industrial complexes worldwide, and contributes to many presentations and published papers on geophysics and leak location technologies, publishing numerous technical papers on the topics. HGI is a solution-oriented geophysical consulting firm and service provider to the environmental engineering, groundwater, mining, and natural resource exploration industries. HGI specializes in the application of geophysical characterization methods, subsurface monitoring of fluids and geological materials, and of course, liner leak location. Please, as you think of questions, please send, there's a tab on there on who to send the question to. Please send it to the organizers and panelists. The speakers at the end of the presentation will address each question in order. The webinar will be recorded and be available on all three companies' websites at the conclusion. So if you have a colleague or someone that couldn't make it, please let them know they can view it on one of the websites. Abigail, when you're ready.
This is the first episode of 7 in a year-long educational webinar series on electrical leak location surveys. Geomembranes are critical for environmental protection. The best way that we have to check geomembranes for leaks before they're put into service is through electricity. How this works is that geomembranes are made of electrically resistive material, different types of plastics. So if we apply electricity across a geomembrane with the current injector above it and the current return electrode below it, electricity will flow through holes in the geomembrane. This is a figure from the ASTM, and it shows a covered method survey. So this power supply here is how we inject current above the geomembrane with the turn electrode, in this case connected to ground, because it's a single geomembrane. This black line is geomembrane here. So the current flows through the leak and only the leak. You'll notice that the cover material is placed just shy of the edge because we need that geomembrane exposed for electrical isolation of the cover material. Now this little apparatus here is measuring voltage throughout the survey area to trace where the current is flowing. There are a handful of ASTM standardized guides and practices for these methods. ASTM D6747 is a guide for the selection of methods, and this covers all of the standard practices. We have 4 different exposed geomembrane standard practices: the water puddle method, ASTM D7002, the waterlands method, ASTM D7703, the arc testing method, ASTM D7953, and the spark testing method, ASTM D7240. The covered geomembranes, that's covered with earth and materials and or water, we have 2 standard practices for those. Both of them can be used for the dipole method. ASTM D7007 is specifically for the dipole method. but ASTM D8265 can be used with the dipole method or other electrical methods that Shawn is actually going to be talking about later on. ASTM D7909 is a guide for the placement of blind actual leaks, which we will talk about in a future webinar. The guide for the selection of methods, ASTM D6747, describes each of the different standard practices that the ASTM has. It also describes permanent monitoring systems. There's no standard practice for permanent monitoring systems. That's the only ASTM document you can go to learn about those systems. And Shawn is going to be talking about those today. This guide provides comparisons between the methodologies. There's a section on it that compares the bare geomembrane methods, which I'm going to talk about today. There's actually a table in there you can go that's really handy reference for the advantages and limitations of each of the types of methodologies. This guide is currently undergoing revision. The last revision was before the publication of ASTM D8265, so that is undergoing revision this year. So let's get into the different exposed geomembrane methods. We're going to talk about how they work. When you understand how they work, you understand why the advantages and limitations are what they are for each methodology. So I like to group the bare geomembrane methods into two categories, water-based and high voltage-based method. The water-based is where the water itself carries the electrical current, and that includes the water puddle and the water lance methods. The high voltage base, the voltage is so high that the electricity actually travels through the air. And those methods include arc testing and spark testing. For all of the methods, the sensitivity is very reliable. You should always be able to detect a pinhole. The leak detection is real time. There's no data acquisition. You just go out and you find the leak. The apparatus usually beeps when it's on a leak. You can pinpoint it and definitely identify exactly where it is. It's a very simple method, but it's extremely operator dependent, and it's also physically difficult to perform. This is a diagram from the ASTM standard practice of the water puddle method. We need a water supply, usually a water truck or a tank, and hoses that can reach throughout the survey area. The hoses connect to the water puddle apparatus to spray the water throughout the survey area. And then we have our power supply. The current electrode, the current injector electrode is connected to the detector electronics, and the return electrode is connected to ground in the case of single liner. And the circuit remains open, so very little to no current flow detected until there's actually a leak in the survey circuit. Then the electrical circuit closes and you get flow of electricity through that circuit, which is then detected by the electronics and converted to an audible beeping sound. This is what that structure looks like. This is one type anyway. There's a hose coming in that feeds water to the water puddle structure. This is a double wide water puddle structure that's about 6 feet or 2 meters wide. And this spray bar applies the water to the geomembrane, and then it's kind of pushed into intimate contact with this roller and spread out, and that roller helps to make sure that water gets throughout the survey area. Here's our detector electronics. We have our electrical line coming in, hooking the power supply to that detector. This is the water lance method. There's no difference in the survey circuit. There's no difference in the electronics or the voltage. It's just a different method of applying the water. So you have a nozzle with laminar flow applying a water jet to the geomembrane. And some people like this because it adds a bit more pressure. So things like pipe penetrations, like you see here, you can't put that water puddle roller around this very easily or at all. So this helps with the sort of strange geometry or slopes that are too steep to walk with the water puddle structure. The water-based exposed geomembrane methods are extremely tolerant of wet and dirty sites. You don't want really large areas of standing water, but it's okay to have scattered puddles. What happens is if there's a leak connected to a puddle, as soon as the water puddle apparatus touches that puddle, you'll get a leak signal. So if there's a leak anywhere in that puddle, you're going to have to evacuate the water to do pinpointing. The leak detection of these methods, it depends on water flow through the hole. So if you have a steep side slope, in my experience, anything steeper than 3 to 1, it starts to get difficult for water to flow through a pinhole. Also, things like repair patches or anything with a tortuous leak path, you need to apply sufficient time and sometimes pressure to force that water to travel through that tortuous path. For these methods, the survey area must have a low spot for water to collect. You can't have water flowing off of the geomembrane, or else that will give you a continuous leak signal throughout the survey. And what's going to happen is you're going to have to turn down the sensitivity on your detector electronics, and you're less likely to find a hole anywhere in the survey area. So you don't want to do that. We want to keep the water inside the survey area. These methods are extremely fast, mainly because of the rollers and how wide they are. Actually, water lance method is not fast, but the water puddle method is the fastest exposed geomembrane method when you have that 2 meter wide or 6 foot wide roller. But these methods do require a water source. It should be a relatively clean water source. You might need to put an inline filter because dirty water will clog those water spray jets. And you must have distribution hoses, which we use garden hoses because they're easy to acquire. The high voltage based methods are very sensitive to moisture. They're somewhat sensitive to dirt, but what dirt does, dirt can actually hide a hole. So if there's like a dry piece of mud over a hole, then that can be missed by the high voltage methods. So you need a clean and very dry survey area. What the moisture does is that it tracks the electricity and it causes the detector electronics to just give an alarm, even though there's no hole there. So we call that a false positive signal. And what the operator has to do is actually turn down the sensitivity if they get too many false positives. And that's going to, again, result in less likely chance of finding all the holes in the survey areas. So the difference between the ARC and the spark testing is that the ARC testing method does not require the specialty geomembrane with the conductive backing. Spark testing is synonymous with conductive backed geomembrane. That's a product that we'll talk about in a couple of slides. The ARC testing method does not work well at all on wrinkles. If you have a liner that has leaked in the past and you have a hole on a wrinkle, you can step on the wrinkle and the back of the geomembrane will kind of coat with mud, and then you could pick up that hole. But if it hasn't leaked yet, you're probably not going to pick up a leak on a wrinkle that's greater than about an inch off the subgrade, or about 2.5 centimeters, because that's the maximum arc length of the instrument. The electricity won't travel through a longer length of air than about an inch. So the geomembrane must maintain intimate contact with the subgrade. So that being said, there might be installations where you have to do the survey at night in order for it to be a good survey if you have lots of wrinkles. So by definition, spark testing is the best method for detecting leaks on wrinkles or other poor contact conditions. I've seen leaks that had non-detects because the subgrade was rutted. So the subgrade was too far away from the bottom of the liner. This is the ASTM diagram of the ARC testing method. So we have a current return electrode in the ground, just like the water puddle method. We have an apparatus that provides high voltage. And again, there's little to no current flow unless you have a leak. And then the electricity goes through that leak like a little lightning bolt. You can actually see it, especially if it's dark out. If it's sunny out, sometimes I'll get somebody to stand there and I'll try to see the little lightning bolt in their shadow. But you can actually see it going through the leak, so it's very easy to pinpoint. This is what one type of ARC testing method apparatus looks like. The main difference between these different testing apparatuses is the probe used. So here you can see I'm using a 1 meter or 3 feet wide neoprene brush. What I like about this one is that it's articulated, so it really conforms really well to the geomembrane surface. It's really crucial to conform to the geomembrane surface. I've used wider brushes, like 5 feet wide, and I can't conform to the surface with such a wide brush. So you want to limit the size of that brush. Moving on to the spark testing method. This method induces a voltage differential across the geomembrane using the pad itself. It's a pulse power supply that gathers the electrons on one side of the geomembrane. So you can only test one panel at a time. And it's the panel that the neoprene grounding pad is sitting on. This method is not going to effectively test fusion welded seams because that conductive backing is sometimes not broken through the fusion weld, so you can get false positives all along that fusion welded seam. There is a method to install a conductive back product that makes all of the liner testable, including these fusion welded seams. And this includes several steps, including the use of this ISO wedge. And this installation method will be discussed by Jimmy in a future webinar. This is the ASTM figure for the spark testing method. So you have your electrically conductive pad sitting on the panel that you're testing. So the electricity is induced by a leak located in the panel that you're testing. I have the word conductive geomembrane in red here because I hear this all the time. People refer to this product as conductive geomembrane. But hopefully you know by now that if the geomembrane were conductive, leak location methods would not work on it because you get false positive signals everywhere throughout the survey area. I like to use conductive backed geomembrane because of the way the product is manufactured. Let's look at it. So this is a cross section of that product. You have an upper insulating layer, if any, sometimes it's white. You have a base insulating layer, that would be the HDPE core, and then on the back side or bottom side, you have the electrically conductive layer. So the entire geomembrane is not conductive, just a portion of it is conductive. And this electrically conductive layer acts as your current carrier for your return. Here's what that instrument looks like. So rather than having a cable that goes all the way to ground, it's connected to this neoprene pad. You have this probe that's made of flexible neoprene that's conductive, so it can conform to the geomembrane surface, and the probe isn't so wide that you can't keep intimate contact with that geomembrane. All of these methods that I just explained to you are technically easy to perform. There's a simple sensitivity adjustment with each instrument, and once you adjust that for site conditions, very little can go wrong while the testing is taking place. Each method has unique advantages and disadvantages, but all of the methods are equally sensitive in the eyes of the ASTM standard practice. They all have to demonstrate that they can locate a pinhole. There is a clause in each one of the standard practices that allow for the use of an alternative method if it's more practical or effective. For example, if arc testing is planned on site and you have an overnight rainstorm, it's probably better to perform a water-based method because otherwise you're going to have to clean and dry the entire liner, and sometimes that's just not practical. Sometimes the methods are combined for maximum effectiveness. What I really like to do with ponds with steep side slopes is to do water puddle method on the floor and then arc testing method on the steep side slopes if it's too steep to walk with water puddle method equipment. All of the methods are very dependent on operator care, and they're physically difficult to do. For the high voltage base, you have to keep that probe in intimate contact with the surface of the geomembrane. For water base, you need to allow sufficient time for infiltration. Sometimes if I'm walking fast with the water puddle instrument, I will hear an increase in signal after I've walked 5 feet past where the leak is. So I hear the increase and then I back up. So it sometimes does take time. Every method needs to be controlled in terms of making sure you have sufficient overlap between the test lanes. Especially for the arc testing and spark testing methods, it's really hard to tell where you've been. With the water methods, you can see the geomembrane is wet where it's been tested, but the arc testing, spark testing don't leave a trail. So it's just difficult to control. A lot of times you need more overlap for those methods that are hard to control. As I said, once equipment functionality is demonstrated, very little can go wrong during testing. The one thing being a cable getting accidentally pulled out. Leaks are very easily pinpointed and visually identified. It's not impossible to miss a leak, but it's typically due to conditions specific to that leak. So if you have a leak on the peak of a wrinkle, the arc testing method might miss that one. If you have a hole that's not large enough for the applied water to get through, like a very small knife slice, I think the water-based methods might miss that. So it's important to understand the technical limitations of each method. And I suggest that you do get some kind of professional recommendation for the method most suitable for your project. However, a leak location contractor will always have in their back pocket that they can change the method if they see that there's a more practical or effective method. They just need the project engineer to agree to change the method. If you have a critical project and you can't tolerate any amount of leakage, conductive back geomembrane product is an option because that enables the detection of leaks on wrinkles and other poor contact situations. However, be mindful of these isolated installation guidelines because if this product is not installed as an isolated geomembrane installation, only the spark testing method can be performed. If it's isolated, you can perform water puddle or dipole or anything on it. So just because you can demonstrate that you can use this method to locate a leak somewhere doesn't mean that you can find a leak anywhere. So these are some of the factors in what I would consider the sensitivity of the method based on the fact that in some situations leaks won't be detected. So you have physical obstacles or penetrations. If you have a conductive penetration, that's the biggest problem for all of the methods. If you have an extreme slope, it's going to be more of a problem for water-based methods. If you don't have a low point for water to collect, it's going to be a problem for the water-based methods. The sensitivity is going to go down for those methods. If you have dirt or moisture present in the survey area, it's going to be more of a problem for the high voltage-based methods. You have to clean and dry that area to get a good test with high voltage-based methods. Wrinkles and other poor contact conditions are going to be a big problem for arc testing, a moderate problem for the water-based because I have been able to apply enough water that water can get through a hole on a wrinkle. But it's not a problem for spark testing because spark testing is used in tandem with that conductive back product. If you have tortuous leak paths, it's basically the same thing as a wrinkle. Not going to be a problem for spark testing, but it's going to be a problem to different degrees for the other methods. So let me tell you a story about repair patches. When the arc testing method first came to the United States, we had a test pad at TRI and we installed 2 different repair patches to see how easily the arc testing method could pick up a leak on extrusion welded repair patch. One patch, we did it with typical HDPE geomembrane, and the other repair patch, we created it with conductive back geomembrane because the conductive backing essentially reduces the travel path for the electricity. That first year that we created these repair patches, the arc testing method was not able to pick up the leak on the typical HDPE repair patch, but it picked it up very easily on the patch with conductive back geomembrane. I asked the manufacturer about this, of the arc testing equipment manufacturer, and they said, oh yeah, you can pick up a leak on a repair patch, you just have to make sure there's humidity inside of the repair patch. Well, the following year, after the pad was subjected to months of varying weather, we went back to both of these patches, and the holes along the extrusion welds were equally detectable on both different type of patches because enough time had gone by that humidity built up inside of the repair patch. So I believe that a newly made repair patch is not testable with the ARC method, that you really need to use a water-based method. Let's move on to some real-life examples. This was the corner of a geomembrane lined tank. They used a prefabricated corner bracket that was welded onto prefabricated L brackets that were welded onto the walls and floor of the tank. The arc testing method did not pick up any leaks here, but the water puddle method did in some of these corners. So the leak path was too tortuous for the arc testing method, but the water puddle method was able to get water through that path. This is a PVC lined tank. Tank was actually a metal walled tank, and we applied the arc testing method here. This is a very small arc testing probe here because of the way the geomembrane sat along the wall, it was very hard to get a wider probe on there and to kind of iron out those wrinkles with a wider probe. So we used a small probe, picked up a very small leak on the wall that was invisible to the naked eye, and then we used the water lance method to jet water at the wall right at that hole location, and I could not detect that hole because it was too small for the water to get through it. This is an example of a conductive penetration. This is impossible to test. So using a conductive penetration is a poor design decision because if this thing is leaking, you're not going to be able to pick it up with these methods. So in this situation, I would use the arc testing method all around the wall, but the arc testing is going to give you a signal when it gets near this metal. The electricity will just zip right to that metal and give you false positives. So you can test all the way around it, but you can't test the penetration itself. This was a penetration that was suspected to be leaking. So we applied the arc testing method, and it easily picked up leaks in these extrusion welds because this penetration had leaked in the past. So it had a wet leak path leading to ground. They actually ripped this out and replaced it with this penetration. So when I was asked to test this, it was brand new, hadn't leaked before. There wasn't enough time for humidity to build up, so I didn't want to use the arc testing method. I used the water puddle method, using a sponge, a handheld sponge, and trying to force water through these extrusion welds. However, sometimes it's best to apply hydraulic head to force water through those leaks, especially if they're small leaks. So this particular penetration, because we were able to electrically isolate it by filling the pipe here with an inflatable bladder, I was actually able to test this using a covered method, the Dipole method, and Shawn is going to talk about that in a couple slides. Let's just do a review of the bare geomembrane methods. So geomembranes are made of electrically resistive materials. So that's what allows us to measure current flow when there's actually a leak in the geomembrane. We apply the electricity on top, we have a current returned below, and the electricity flows through the leak. It completes the circuit. It causes current to flow when there is a leak in the circuit. The water puddle and water lens methods are water-based, where the water carries the current. The arc testing and the spark testing are high voltage based, where the air carries the current. All of these are highly sensitive and very reliable to detect pinhole-sized leaks. They all have advantages and limitations, which hopefully you understand now, but they're all technically easy to perform. The condition of the geomembrane affects the method choice and the sensitivity of the method. So if you have obstacles, penetrations, slopes, dirt, moisture, all of these are going to make it difficult to make sure you detect leaks everywhere in the area. It's easy to demonstrate you can detect a leak in one location, but it's a field challenge to make sure that you can apply that same sensitivity everywhere throughout the survey area. So with that, I'm going to pass you over to Shawn, and he's going to talk about the covered geomembrane methods.
Thank you, Abigail. That was a wonderful beginning to our webinar series. Again, my name is Shawn Calendine. I'm with Hydrogeophysics, and like Abigail with TRI, one of HGI's signature services is liner leak location, and that is why we are here talking to you today. For the remainder of our discussion today, we are going to give you a brief preview of future episodes in the ELL webinar series. As we move forward, keep in mind that while a specific episode may focus on a particular method, we will also discuss related ELL techniques in each episode so that we can compare, contrast, and better explain all leak location technologies throughout this series. Covered geomembrane methods are covered in episodes 2, 3, and 4. These methods are highly technical and require an understanding of electrical current as it is applied to the materials covering geomembrane liners. In these episodes, we will examine current injection into these materials and liquids, discuss current pathways, and its return to the underlying conductive layer through holes in the liner. We will also explore the critical nature of area isolation and its impact on electrical leak location signals associated with holes. We will discuss how and why current is always flowing during the leak location process for covered liners. And we will look into the many different methods and techniques used to map current flow throughout cover materials to locate leaks. The water-covered dipole method for liner leak location will be covered in episode 2. Here we will focus on water-covered weighting surveys using a dipole probe. In this episode, we will help webinar attendees understand how current is applied to liquid for leak location. We will discuss sensitivity relating to leak size, solution conductivity, and survey geometry. We will go over site preparation related to electrical isolation of the structure, also known as structural boundary conditions, and look into different methods for different liner and facility configurations. For episode 3, we will discuss the soil-covered dipole method. We will look into both ASTM D7007 electrical methods for locating leaks in geomembranes covered with water or earth materials, and ASTM D8265 electrical methods for mapping leaks in installed geomembranes. In this episode, we will look into survey preparation and setup, discuss isolation requirements for soil-covered surveys, understand how current is applied to soil covers for leak location, look into artificial leak location procedures and the difference between actual and artificial leaks, go over the ASTM D7909, the blind leak guide, examine leak detection distance testing to determine leak signal and background noise, discuss data analysis, which is a critical part of the leak location process, look at different styles of data presentation, and outline reporting procedures to make sure reports include survey results with actionable information that is clearly understood. In episode 4, we will focus on deeply filled and large industrial ponds. We will review leak location concepts for water-covered containment structures from episode 2, discuss the fundamentals of electric current, analyze current flow through different types of solutions, and how some of those solutions can affect leak location sensitivity. In this episode, we will discuss the high level of expertise required to perform these types of surveys, how the method works for single and double line systems, analyze sensitivity relative to on-site conditions, survey geometry, and area infrastructure, recognize how poor site conditions can affect leak location efforts, and understand the concept of signal shadowing. This is the concept where a high current density associated with a large hole in a liner can obscure smaller holes with smaller leak signals within the electrical shadow of the larger hole. And finally, review leak detection accuracy as a function of solution conductivity. Permanent monitoring systems. Now I would like to take a moment and discuss permanent monitoring systems. This is the only time throughout the ELL series that we will mention this topic. The reason is because there is currently no ASTM standard for permanent monitoring systems, and they are used rather limitedly due to their cost and need. These systems are primarily guided by risk. That is, applications where risk of leaks during operation is high and contain solutions and materials are dangerous and toxic. This image is an example of risk associated with large containment structures. This image shows the extent of a plume that leaked from a subsurface structure known as a vault. The structure was built in the 1950s as a storage and transfer station for various waste streams transferring to process tanks at the Hanford nuclear site. The image was produced by Hydrogeophysics and published on the cover of the American Nuclear Society's Rad Waste Solutions publication. Permanent monitoring systems. Permanent monitoring allows for continuous monitoring of leaks for the life of the detection system or the life of the containment system. Both systems are unique and different in complexity, and one may actually outlast the other. Thus, a monitoring system will only function for as long as the components last. There is no standard for this. The constituents, fluids, and solids can be highly corrosive, and the components used for long-term monitoring have to withstand the destructive properties of the material they monitor. Developing components that can live in these extreme environments is technically challenging and costly. These methods are typically designed to monitor for leaks 24/7 and have alert systems that are communicated through a computer monitoring system when a leak signal is detected. Detection accuracy depends on the type of sensor technology that is developed, sensor spacing, and sensor placement. These types of monitoring systems are not common due to the high cost of the technology, installation, and complexity of these systems. For geomembrane line systems, the technology is based on permanent sensors installed in a grid pattern either above the secondary geomembrane, between the primary and secondary geomembrane, or beneath the primary geomembrane, and this all takes place during construction. These sensors are connected to cables leading to a central computer system where they are monitored for leaks. Here is an example of a permanent monitoring data acquisition leak detection system. The system is built by Texplore, and the photo comes courtesy of Solmax. This is an example of a permanent monitoring leak location sensor by Texplore. Photo courtesy of Solmax. Note the small square piece of metal in the center. It is made to be resistive to corrosive solutions and contained in a plastic housing that can be welded to the surface of a geomembrane. There are many different types and styles of permanent monitoring sensors. They could also exist as a metal rod, disc, wire, or some type of metal component. The metal is corrosion-resistant materials typically made of some type of metal alloy. The sensors are connected via a wire housed in a chemical-resistant plastic, leading to a central computer. This is an example of wires leading to leak location sensors on the surface of a geomembrane-lined containment facility. They are collected at a central location and connected to a data acquisition system. These wires could also house leak location sensors as embedded sensors in cables, and then distributed across the facility to be monitored. Photo courtesy of iCorp. This is an example of a permanent monitoring system built by Hydrogeophysics for subsurface nuclear waste tanks at the Hanford nuclear site. The system works because electrical current moves more readily through wet soil than dry. The current is introduced into the earth from one sensor, and the resistance of the received current is measured on all other sensors surrounding the tank. Data is acquired continually and analyzed for changes in the electrical resistivity of the subsurface soils that surrounds these structures. If a leak occurs, the resistivity of the soil associated with the leak will change, becoming more conductive. A measurement threshold will be broken, and an alarm will alert operators that the tank may be in a leak situation. The sensors consist of surface-based electrodes intruding 6 to 8 inches into the ground, steel-cased monitoring wells acting as long electrodes, and electrode chains down boreholes with multiple sensors at depth. One type of sensor or a combination of all sensors can be used. This method does not offer pinpoint leak location accuracy. Rather, it offers a binary leak or no leak scenario, as Zero leaks are the goal due to the toxicity and danger of the constituents in the tank. However, the system is sensitive enough to target a leak location to a specific area of the tank, and in a blind test on a mock tank, scientists at HGI were able to estimate the volume of material leaked to within 14% of the actual volume released. Image courtesy of hydrogeophysics. Now, on to the remaining episodes for preview. In episode 5, we will discuss the operator's guide to electric leak location site preparation. Client preparation for this type of survey is incredibly important. A broad level of cooperation with survey providers will be necessary for site owners and operators to prepare for a leak location survey. In this session, we will cover scheduling considerations such as weather, site schedules, and related scheduling issues. For example, weather could hold up a pond survey if a pond is frozen. This is because most of the leak location methods work by having leak detection sensors as close as possible to the surface of the liner. We will also discuss site location and structure conditions. For example, it is critical to understand all aspects of site location as preparation for a survey on a facility located at an elevation of 11,000 feet would be organized differently than a survey at sea level for a structure located in the desert. Survey design questions will be reviewed to help clients understand why structure size, shape, and related infrastructure associated with the site can impact survey organization, setup, and survey timelines. One of the most important pieces of the preparation puzzle is health and safety. We will go over what to include in a health and safety package for both the survey provider and the client, as safety requirements are highly specific to individual sites. A sewage treatment plant needing a leak location survey, for example, will have a much different requirement than, say, a mining site. The sewage treatment plant would be covered under OSHA, and the mining site would be covered under MSHA. Lastly, we will help attendees understand the all-important need for electrical isolation and discuss isolation action items needed before a leak location survey is performed. In episode 6, Abigail will discuss designing for minimizing or eliminating leakage. Here, she will cover specifying methods for various liner configurations, such as testing double-line facilities. Then look into specifying methods for meeting design goals, such as allowable leakage rates, calculating risks of exceeding a specified leak rate, and properly specifying ELL methods for project specifications. And finally, 1 year from now, we will have our final episode in January of 2022, episode 7, the ELL case study panel session. The panel will include industry experts, with each delivering a short case study illustrating lessons learned during leak location surveys. Case studies presented may be importance of survey area isolation, how multiple, large, and an excessive number of leaks can affect survey results, the importance of site materials and material condition at the time of survey, the importance of proper method selection, and other lessons and experiences gained from purveyors in our industry. We would all like to thank you for attending the presentation today, the first episode in the joint educational series produced in cooperation with Solmax, TRI, and Hydrogeophysics. We all hope that you will attend future episodes of this series, and should you know of anyone needing liner leak location or wanting to learn more about the liner leak location technology, please pass this video on to them. Now we will discuss questions.
That's a great question. For those of us who use water puddle method, we'll say it's the best method. For those of us who only use arc testing method, we'll say it's the best method. Because you always see that method like what on the day it's most effective, and it blows you away at how small of a hole it can find. For those of us who use both and any and all method, almost all of us prefer the water puddle method. Because there's always that site where like you visually see a hole and the arc tester won't pick it up because the hole's like not quite in contact with the subgrade or something. So we love the water puddle method.
They're talking about on a conductive backliner.
I know,
the water methods in Spartan. testing. Okay.
Yeah. So I would love to use a water puddle method on anything, except the problem is if that conductive back liner is not installed as an electrically isolated installation, you can't use water puddle method. Because what's going to happen is that your water puddle is going to ground out on every single one of those overlap flaps. So you have to use the spark testing method if the isolation guidelines aren't followed. If the isolation guidelines are followed, there's no reason why you can't do water puddle method. That's the whole point of the isolated installation is to be able to use all methods on it. Whether directly comparing the spark test to the water puddle on conductive back material, I've never heard that. This is a really good question. I think that the water puddle method would be better. The reason is because it's going to have a direct connection to the underlying conductive layer. It doesn't rely on the induction of the pad to create that differential, and you can kind of force water to completely cover the surface, but the spark testing method, you have to really take a lot of care in getting intimate contact with the surface. So I believe the water puddle method, but you have to install it as an isolated installation.
The only experience I've had with that, Abigail, with the smaller holes, if the water goes through the hole in time before you move on.
Yeah, it's a great point. And that's why it's like, okay, yeah, you might prefer the water puddle for this reason, but I agree with Jimmy. When I first started using the first spark testing project I ever had, I found this hole that was so small it blew me away. It was like an 1/8 inch long knife slice, and I knew that water would not get through that hole. So yeah, if you want to make sure it gets through every little hole, then a high voltage method is definitely better. Yeah, so here's the deal with the GCL. It comes out of the factory sufficiently moist for testing. And when it's set on subgrade, it really wicks the moisture from the subgrade. The problem with GCL is when, so to answer your question, yes, it usually will conduct the electricity well enough. The problem is when it's used as a primary GCL in a double line containment facility. I call that encapsulated GCL, where you have a secondary geomembrane, GCL, primary geomembrane. If that GCL is deployed in a very arid environment and it's not covered right away with primary geomembrane, it easily dries out to the point where it's no longer electrically conductive. Once that primary goes down, we cannot test the primary because the GCL is desiccated to the point where it won't carry the current. So it's really important to take note of that if you have a double line facility where you want to test the primary and the only thing between those two geomembranes is the GCL. So HDPE is more electrically insulative than the other types of liners, but that doesn't mean the other types of liners won't work. So something like PVC or the other flexible geomembranes, what I really like about them is that they're less wrinkly. And also you can work those wrinkles out by stepping on them. That's a huge advantage for leak location. And they are sufficiently electrically resistive. The one time you might have a problem is when you're applying high voltage methods onto some of the flexible geomembrane products. The ones that I've subjected it to, it works. But I just want to put a warning out there. If it's a product that you're not familiar with or you haven't tested before and it's extremely thin, then you want to perform our testing method, you might just want to ask for a sample of it, make sure it still works on there. What happens is that it'll give you false positives everywhere on that if it's not thick enough or resistive enough. But usually in most common materials that I've been exposed to, no problems with testing other materials.
Yeah, if I could just jump in there really quick, the vast majority of these materials are extremely electrically resistive, as Abigail said. And fundamentally, that's why this technology works, right? Because, current can't flow through it. Therefore, when it finds a hole that, the current wants to go to ground, and, we're able to see those current highs over the leaks. So the fundamental fact that these materials are highly resistive is specifically why this works in the first place.
A good question. It depends on the method. Arc testing method is, I'm going to say English units, so I can't do the metric. We can arc test about 1.5 acres a day. We can water puddle test 4 to 6 acres a day. We can soil dipole test at least 5 acres a day. I usually say 5 to 8, but we can sometimes do 10 on a long day. Dipole in water, we're a little bit slower in like 4 acres a day. So Shawn, can you answer that for a filled pond? How long does it take you guys to test one of those?
For like a great big pond, yeah. Again, it depends on the size of the pond and where it's located. If it's a small pond, say around 1 acre, it can take a day or maybe 2. For much larger ponds, you're looking at anywhere from 3 or 4 days to as much as a week or more. So it's really dependent upon size and the method that you're going to use for these deeply filled ponds.
Absolutely. I was on a site 2 weeks ago where found a hole, repaired it with extrusion welded patch. They vacuum tested it. I came in, didn't pass my test. There was current flowing through that patch. I think they tried 8 times before they just gave up and redid the repair. It's pretty common for the water puddle method to be able to detect leaks that the vacuum box can't. I don't totally know why that is, but I've seen it multiple times. So